Okay, let's calculate what is weightlessness. There's no such thing as microgravity first. Gravity is everywhere a mass is located. There is also up and down in space. Down is towards the largest mass, and up is away from the largest mass. So let's investigate this. Let's calculate what is weightlessness. First, let's calculate weight on Earth. It's incorrect to say that there's no gravity in space because there is gravity in space, and the Earth's gravity is pulling downwards on astronauts. But the key is that if you're orbiting the Earth or orbiting any other body, that means you have a tangential velocity that changes direction as you orbit the Earth, causing you to circle the Earth. Therefore, you feel weightless and float because you will be continuously falling around the Earth. Okay, so what is gravity on Earth? To make this as simple as possible, let's assume the Earth is a perfect sphere. Really, due to rotational effects, the Earth is an oblate spheroid, or somewhat egg-shaped. But for our calculations, we're going to say that the Earth is a perfect sphere. So from the center of the Earth to the surface of the Earth, we calculate as 6.37 kilometers, and which is approximately 3,959 miles, okay? And the mass of the Earth we calculate as 5.97 times 10 to the 24th kilograms, which is approximately 1.325 times 10 to the 25th pounds. Isaac Newton said the equation of gravity. Isaac Newton's law of gravitation says that all bodies attract each other with the following force. The force of gravity is equal to G, which is a constant, times M1 times M2, two masses, divided by the radius of their separation from their centers squared. Okay? So where G is equal to 6.67 times 10 to the minus 11 cubic meters divided by kilograms divided by seconds squared. G was measured by Henry Cavendish, who was born in October 10th, 1731. It's known as the Cavendish experiment, performed in 1798. 1798. They didn't have calculators then. 2014, we have calculators. What are you doing with your calculator? Huh. Okay, let's say we had 1 kilogram sitting on the Earth, which isn't much. Okay, but it's sitting on the top of the Earth. So we call this 1 kilogram mass 1, and we call Earth mass 2. Okay, so we now know the radius here, and we now know the mass of the Earth. Okay, so let's continue. Isaac Newton also said that a force on a body is equal to its mass times acceleration, its acceleration of gravity. So this force is equal to M1 times A gravity, acceleration of gravity. So for 1 kilogram mass sitting on the Earth, the gravitational attraction G is the force of gravity pulling between the two masses, and that's equal to the force of acceleration of the mass 1 times gravity. So if we set those two equal to each other, okay, when we solve for G, we get small g. We solve for small g of gravity, we get the large g of the constant times mass 2 divided by the radius of separation squared. Okay, so the M1s cancel. As you can see, when we set these two equations together, M1 cancels. That's the mass on top of the Earth. So if we solve for G here, G is equal to 6.67 times 10 to the minus 11th, which is G, large G, the G constant. We say mass 1 cancels, so mass 2 is equal to mass of the Earth, and the radius of separation is essentially from the center of the Earth to the surface of the Earth, which is 6.37 times 10 to the 6 meters. And if we do that calculation, we get 9.81 meters per second squared in SI units. Okay, but in our units we use in the United States, English units, feet in seconds squared. If you change the units on that, it comes out to 32.17 feet per second squared. Your weight on Earth. Therefore, when you weigh yourself on Earth by standing on a bathroom scale, your body is attracted to the Earth by this acceleration. Force equals m1 times g gravity. And you're m1, okay? So if you weigh 180 pounds on the scale, your mass is force, which is 180 pounds, divided by 32.2 feet per second squared. That gives 5.59 pounds second squared divided by foot, which is equal to 5.59 slugs. Slugs? What in the heck is a slug? Oh boy. You see, this is English units based on a avoirdupois pound and the English foot. How do you pronounce that? Well, here's the pronunciation. Okay. So let's use international units of kilograms and meters. So if you weigh 180 pounds on the scale, your force in newtons is 180 pounds times 4.44822 newtons per pound. And you multiply those two numbers, you get 800.68 newtons. And then if you divide 800.68 newtons by 9.81 meters per second squared, you get 81.62 kilograms. So your mass is 81.62 kilograms. This is the mass on Earth, in space, on the moon, on Mars, and anywhere in the universe. So you see, on Earth, you're not really measuring your weight. You're really measuring your mass and multiplying it by the gravitational attraction of Earth. That's why if you're on another planet, your weight is different because each planet has a different gravitational attraction. On the moon, the gravitational attraction is approximately 1/6 that of Earth. So briefly, how is this done? Let's see. So you weigh 180 pounds on a scale on Earth. You go in your bathroom, you step on the scale, and your force in newtons is 180 pounds. Now, your bathroom scale won't give you 180 newtons, 180 pounds. It won't give it to you in newtons, it gives it to you in pounds. So you have to convert pounds to newtons. So you multiply 180 pounds times 4.4482 newtons per pound, and you get 800.68 newtons. And then you divide that newtons by 9.81, and you get 81.62 kilograms, and that's it. That's your mass. So if you're on the moon, your weight is 1/6 of that. So you got your same mass times 1/6 times 9.81 equals 133.45 newtons. And then you change newtons to pounds, and you divide newtons, 4.44822 newtons into 133.45, and you get 30 pounds. So if you weigh 180 pounds on Earth, you weigh 30 pounds on the moon. And that's how it's done. Now that we got that out of the way, let's look at the elevator. Okay, elevator going up. Let's say you're in an elevator standing on a bathroom scale. And this is a great experiment to do. Let's say you're on an elevator and you're standing on a bathroom scale and the elevator accelerates up. Okay, here's our elevator. And here's the cable that pulls you up on the elevator. And you're standing on a bathroom scale. Okay. The force of gravity, your mass times gravity, is pulling down on you. And while you're standing on the bathroom scale, the scale is pushing back up on you, because whatever you push, it pushes back towards you. Okay, so the bathroom scale is pushing up on you. So you have a force pushing up on you from the scale, and your mass times gravity is pushing down on the scale. Okay, and A is equal to acceleration of the elevator. So the elevator is going up, so it's accelerating up. Okay. So, again, Fs is the force of the scale pushing up on you. That ringing you heard was my telephone telling me it's time for something else. And mg equals your mass times gravity pushing down. G is gravitational attraction, 9.81 meters per second squared. Okay, so if we sum our forces in the up direction, which is up is plus, right there. So F scale plus minus mg, and all of that's got to be equal to the mass times the acceleration up. And if we solve that equation and we factor out mass, we get m times quantity a plus g. What that says is, as the elevator accelerates upward, you gain weight. So if you're standing on a bathroom scale in the elevator and you press the top floor and the elevator takes off and you weigh 180 pounds, when that elevator takes off, you're going to see something larger than 180 pounds on that bathroom scale. You're going to gain weight. That's a great experiment, okay? Let's say the elevator is going down. Let's say you're standing on the bathroom scale and the elevator is going down. Okay, we have our same equations here, okay? But this time, down is positive, okay? So now F scale is negative plus mg is positive is equal to mass times acceleration of the elevator. So if we solve our equation for F scale, we see that F scale is equal to m times the quantity g minus a. Oh boy. Therefore, as the elevator accelerates downward, you lose weight. Isn't that amazing? So that would be a great experiment. If you're on the, let's say, the 6th floor of of a building, and you feel like you're overweight, all you have to do is bring a bathroom scale with you, get on the elevator, stand on the elevator, press down to the bottom floor, and for how many floors you go down, you will lose weight. Isn't that amazing? Okay, one more. The elevator cable's cut. Let's say you're in an elevator standing on the bathroom scale, and all of a sudden the cable to the elevator is cut, and you start screamingly advancing towards the 1st floor. Let's say you're on the 11th floor. Oh, God forbid. Okay, we have our same equations here, but this time mass times acceleration of the elevator, the acceleration is equal to g. So therefore, force F scale is equal to mass times g minus g, which is 0. Therefore, you're weightless and you float inside the elevator, falling with the elevator at a velocity v for a height h for t seconds. And here's that equation right here. Okay. 9.8 meters per second times g times t. Okay. And this velocity free fall is a negative velocity. Okay, you're going down. Hopefully, you don't drop too far. And you fall for a height h, 1/2 times gravity times t squared. Okay, if you want to calculate your height, how far you fall. Okay, but most elevators and cables don't break because they have emergency brakes. Okay, so you won't have any problems with that. You won't fall very far. Okay. Now that we got that out of the way, let's look at how astronauts train for weightlessness. Okay, let's see how astronauts train for weightlessness. Okay, when I was working at NASA, there was a plane called KC-135. And the KC-135 would take astronauts up to about 30,000 feet. And then it would follow parabolic loops to where they would experience weightlessness. And so I'm going to explain how that was done. Okay, this KC-135 would reach a certain point, and then it would cut the engines at this point right here. It would be traveling at 425 miles per hour, or approximately 189.99 meters per second squared. We're going to use SI units instead of miles per hour. So at this point, it would cut all the engines, okay? And what would happen then is, in the vertical direction, the plane would be traveling 134.34 meters per second. In the horizontal direction, the plane would be traveling 134.34 meters per second. The reason why they're the same is because I use 45-degree angle here. And there's nothing special about the angle. It could have been any angle. But I use 45-degree angle, so they both come out the same. Okay. So once the pilot cut the engines, turned off the engines, the plane is still traveling at 134.34 meters per second in the upward direction. But what happens is the plane is going up and is losing velocity, going up. And at this point, it reaches zero upward velocity. And then the plane would fall back to Earth. And then it would get to this point here, and it would have the same velocity as it had when it left over here. Okay? So it would start off at 134.34 meters per second, and then that upward velocity would go to zero, then would fall back down, and would get the same velocity it had over here. Okay? Then once it got here, this engines would start again, the plane would continue on down, and it would level off, and then it would take off for another loop, and the engines would cut again here, and then the plane would take off and go up to zero velocity again. And they'd do about 40 loops. And that's how the KC-135 would allow the astronauts to experience weightlessness. And the weightlessness would occur within these two halves, okay? Because according to the equation of motion, if you calculate the time between here and here, where zero velocity is occurring, that's about approximately 13.69 seconds. And over on this side, is approximately 13.69 seconds. So that's approximately 27, 28 seconds of weightlessness. Okay? And that's how that's done. Okay, KC-135 parabolic loops. That's like jumping up and down on a trampoline. Okay? As we discussed before, when we looked at the graph, the KC-135 would take off here and go up to zero velocity, vertical velocity, and fall back down. Okay? The right side of the parabola, which is Vy, vertical velocity, is equal to 134.34 minus GT. Okay? So for every second you're going up, you lose this velocity until this Vy would get to zero right here. Okay? On the right side, when you're falling back down, the free fall side of parabola is equal to minus G times T. Okay? So for every second you fall, you would get that negative velocity falling down. Okay? And if you calculate the times between these, it's 13.69 on this side, 13.69 seconds on this side, for a total of 27.39 seconds of weightlessness. That's just like jumping up and down on a trampoline. As you jump down on the trampoline, you bend your legs and propel yourself upward. Okay, you're weightless. And as you reach to the top of your height, you stop and you fall back down towards the trampoline at the same velocity that you left the trampoline. And that's the same with anything. That's why it shouldn't be, a pistol shouldn't be fired inside of city limits. Because for one thing, it's illegal. And for the second thing is, when you fire a pistol bullet into the air, that bullet leaves that pistol at a certain velocity. When that bullet reaches its height, it falls back to Earth. When it falls back to Earth, it falls back at the same velocity that it left your pistol. So if you don't know where that bullet's going, it's best you leave your pistol in the house, which you shouldn't have one anyway, because I don't believe in pistols. So anyway, that's it. Now, well, we saw the graphic already, so here is the vomit comment. Below are videos of how weightlessness is achieved on Earth. So if you look at these videos, you'll see the KC-135 and some other videos of airplanes that go through these parabolic loops, and you'll see how weightlessness is achieved. Thanks for tuning in, and until next time, I hope you had some fun.